Hi, welcome to our YouTube channel. My name is Edward, and with my friend Edwin, we will use this channel to explain some of our programming projects. In today's series, Programming Autonomous Cars, we will release a series of videos exploring neural networks and how they can be used to teach cars to drive autonomously. By the end of the series, we will hopefully be able to develop a program that can teach cars to drive autonomously given any obstacle course. We will be using Unity to design an interface to display our cars and obstacle course. In this video today, we'll be exploring neural networks and how we can implement them. So, what are neural networks? Neural networks are algorithms or programs that are modeled after the human brain. Through sensory data and input, neural networks are designed to recognize different patterns. By identifying patterns, neural networks can teach a network how to respond. On a more general level, neural networks can be seen as a component of machine learning, heavily connected to subjects like reinforcement learning and classification. Some examples that come to mind of the implementation of neural networks include sales forecasting and facial recognition. So now that we have a general idea of what neural networks are, let's look a bit at the conceptual logic. So neural networks can be programmed in a variety of different ways, but for now, we'll take a very simple look at a single layer neural network. So, to begin, neural networks are composed of nodes or layers of nodes. Nodes are often referred to as neurons or computational units. And nodes interpret input and they produce some sort of output based on the input. Together, a series of nodes can be organized to make a network. So let's take a look at this diagram of a node. So in this neural network, you see how each node is connected. One variable enters as input, and an output is returned from the node after some calculations. In this diagram, we can read it from left to right. Each vertical line of nodes is referred to as a layer. Neural networks are distinguished by their depth or the number of layers there are. We're going to take a look at a perceptron, a single layer network. It takes in inputs, processes the information, and produces some sort of output corresponding to the input. So by connecting to these neurons, we can receive more complex inputs and obviously produce more complex outputs, like identifying the differences between a cat and dogs. So let's take a look at how a neuron interprets this input. In order to make connections between the input, like the shape of a dog's face, weights are assigned to an input. The first calculation the neuron does is it finds the total sum of the weights. If the node has two inputs, there are two weights, and so it would find the total sum of each weight multiplied by its input. So input 1 times weight 1 plus input 2 times weight 2. Okay, hopefully that wasn't too confusing. Now let's talk about the second step, the activation function. Next, we have an activation function, and this activation function calculates what class this input identifies in. There are a lot of different activation functions. For example, step functions, which cause the neuron to output X value if the summation of weights is higher than a certain threshold, and that's what most simple perceptrons use. So there are multiple ways to determine the weights of each connection, through guess and check, machine learning, and etc. So let's try an example problem right now. We don't need to write any code. We'll try and explore some more logic behind the perceptron. So our boss has contacted us, and we need to use our perceptron to be able to identify two different groups, puppies and grown-up dogs. Each group is differentiated by their different inputs, their height, and the age of the dog. So let's say, for example, a puppy is considered a puppy when it is less than 15 months old, and a puppy also has to be less than 30 centimeters. We can graph this out to get a better understanding of how to classify the two different groups. So you can look at this graph right here. Everything under the red area can be considered a puppy. Outside the area, all these data points can be considered dogs. So for this question, this is a linearly separable problem. So what does this mean? It's an extremely simple problem. The perceptron should be able to solve this in 2 to 3 generations because of the simplicity of the problem. Because as you see with the line, all the data is separated into two different groups outside the line. if a perceptron were to solve a non-linearly separable problem. For example, if there was a circle and inside the circle is one group and outside the circle there's another group. So this is an example of a non-linearly separable problem, but in this case we have a linearly separable problem. So for our perceptron we have two inputs, the height and the age of our puppies. So the perceptron should only produce two outputs, -1 if it's a puppy and 1 if it's a dog. So we can train our perceptron accordingly. So we have our input, we know what is correct, and we can train our perceptron because we know exactly what is right or wrong. We know that inside the area those are puppies and outside the area those are dogs. So we need an indicator to show us how well our perceptron is performing. So we use a concept called error. This error is calculated by the difference between the desired answer and the answer provided by the perceptron. Like we said before, there are two outputs, negative and 1. And the correct answer is either -1 or 1, and the perceptron only outputs -1 and 1. Since only have two different types of outputs, there are only 3 different error values, 0, +2, and -2. So we need to train our perceptron now. So we have an error which tells us whether our perceptron is wrong or right. There are many different ways you can train a perceptron. We want to use an evolving neural network to train our cars, so we will be using a genetic algorithm to train our perceptron. So our genetic algorithm will imitate sexual reproduction. So there will be multiple generations of the perceptron, and each generation will try to learn from its last. So if we look at nature in general terms, sexual reproduction is basically how new organisms are created. The genetic material from the parents are passed down to the child, and there are two parents, and then it's passed down to the next child, and the child is the next generation. So this is exactly what our algorithm should imitate. We'll also use a bit of natural selection to determine which perceptron performs the best. So the general logic here is we want to create a lot of different perceptrons, create a new population of perceptrons, and each has a random weight for the input. We find the 2 best performing perceptrons, each with the lowest cumulative error. So we can find the lowest cumulative error by adding up the absolute value of the error. Whichever perceptron has the lowest error value is the best one. So we find the 2 best performing perceptrons, and these perceptrons will be selected as the parents for the next generation of perceptrons. So when we're generating the 2 parents, we need to note down the value of their weights. So when we determine the weights of the child, there is a probability that the weights of the child are the same as their parents. So there will be a 50% chance that child ends up with a weight from either of its parents. So, however, we have to add a mutation, which is an alteration of the normal genetic sequence. The mutation can have a 2 to 3% chance of happening. When a mutation occurs, a random weight is generated to the child of the parents. We need mutations because it's always possible that the weights of the parents are not the most ideal or effective weights. Without mutations, we would only have children or perceptrons who have permutations of weights from the previous generation. So we want to produce a significant amount of children so that mutations happen. So to execute the algorithm, we first produce a population of perceptrons with random weights, as many as you want to produce. Select the 2 best performing perceptrons with the lowest cumulative error, and you can produce the same amount of children as parents. This process repeats over and over again until you are satisfied with the results or the perceptron can successfully evolve. So that was the first video of our series today. Hopefully the content wasn't too dull. Stay tuned for the next video and subscribe if you enjoyed.